Welcome to section 14.7. This is Divergence and Stokes Theorems examples. Let's first start off with an example of the divergence theorem using Flux. So let's let F be the vector field y times x squared, comma, x times y squared minus 3z to the fourth, comma, x cubed plus y squared. And S is a sphere with radius 4. And z is bounded above by 0 and y is bounded above by 0. So this is an octant of the sphere. So if we think about, we have a sphere here, it's this lower kind of octant in this bottom part of the sphere here. So we have only a portion of the sphere, so we have to consider that when we're working on this problem. So we're looking for flux. So flux in three-dimensional space. So think about, can you use the divergence theorem? So looking at the divergence over this domain, this is a closed bounded region. The sphere itself is closed and we are bounding it. And so we're still containing a closed bounded region here. So the divergence of F is equal to 2xy plus 2xy plus 0, which is equal to 4xy. Now we need to describe the bounds for D. And so we're dealing with the sphere, so it makes sense to look at spherical coordinates here. Spherical coordinates. So if we're representing our bounds with in spherical coordinates, let's recall that rho squared is equal to x squared plus y squared plus z squared. X is equal to rho cosine phi, or typically speaking we do x is equal to rho sine phi cosine theta, y is equal to rho sine phi sine theta, and z is equal to rho cosine phi. And our Jacobian here is equal to rho squared sine phi d rho d phi d theta. So we will need these components for our problem. So we have to consider our spherical coordinates. So we know that we're looking at radius 4 and we have bounds on our z and our y components. So if we think about what our x and our y components are looking like, so our radius is 4, so we have rho as an element from 0 to 4. We start at the center and go out to 4. However, because our y is bounded less than 0, this means that our theta has to be bounded by lower bound of pi and upper bound of 2 pi, because our y is the back half of the sphere. And then our z is the lower bound, so that means that our phi has to be underneath the halfway mark. So pi over 2 is our lower bound for phi, and up pi is our upper bound for phi. So again, remember with spherical coordinates, rho goes out, theta goes around, and phi is the angle going down. And again, this could be different based on your engineering courses as well. The switch up between theta and phi, so keep that in mind. So for our divergence theorem, we have our coordinate system set up. So all we need to do is evaluate the integral. So we have pi to 2 pi, pi over 2 to pi, 0 to 4, that's our domain. And then 4 rho sine phi cosine theta, that's our x component, and our y component, rho sine phi sine theta. This is our vector field F, or excuse me, the divergence of F. And then we multiply by the Jacobian times rho squared sine of phi d rho d phi d theta. And this is our Jacobian. And so now we can go through and work this problem. So notice these bounds are all constant, so this integral is separable, so we can break this into chunks. So let's separate out all the pieces that have theta in it. So we can separate out cosine theta and sine theta d theta. This is multiplied. This turns out to be a constant, so we can essentially pull it out front as if it's a constant. These are what we call separable integrals. We can do the same thing as sine of phi. There's 3 of them, so we'll cube it. Sine of phi d phi. And rho, we'll keep that 0 to 4, and we'll keep that 4 rho to the 4th d rho. So the benefit of evaluating these integrals separately is that you start to, if one of these integrals equals 0, then the entire integral equals 0. So the first integral is easy to solve. We know that's not going to equal 0. But let's go ahead and solve this. So this first integral here, so this becomes 4/5 rho to the 5th, evaluated from 0 to 4. And so moving down the line, this gives us 4 to the 6th over 5. In our first integral, this is a U-substitution. So if I let U equal sine of theta, du equals cosine of theta, d theta. So I know my antiderivative is negative cosine of theta, evaluated from pi to 2 pi. So I get negative cosine of 2 pi is negative 1. And then I subtract off negative cosine of pi, which is negative 1. So I get negative 1 minus positive 1, which I get is negative 2. Negative 1, let's see, minus 1 is negative 2. And then on the inside piece here, we get, you can make a transformation of sine of theta times 1 minus cosine squared of theta, using the property that this is sine times sine squared, and then sine squared is 1 minus cosine squared. And then we can say u is equal to cosine of theta, or excuse me, cosine of phi. So du is equal to negative sine of phi. So when we do this, we get cosine of phi minus, we need a negative out front. So negative cosine of phi, the du phi, minus cosine, excuse me, 1/3 cosine cubed of phi. And so this is evaluated from pi over 2 to pi. So at pi over 2, or excuse me, at pi, this is negative. So pi is negative 1 minus 1/3, but so that becomes plus 1/3. And at pi over 2, cosine of phi is 0, so that drops off. So then we have negative 2 times negative 2/3. So that becomes a positive 2/3 times 4/6 over 5. So this turns out to be a negative 4 to the 7th over 15 as our solution for the flux on this integral. So let's do another example here. So let's look at finding the curl on the surface. So where the surface is given by x equals 6 minus 4y squared minus 4z squared, This is a paraboloid that lives in front of x equals -2 with orientation in the negative x-axis direction. So if we have this surface, this is a closed bounded surface, we have a vector field. If we can define the edge between where these surfaces meet, then we can find the circulation along that boundary area. So let's first define the curve. So define the curve C of the intersection. So first we need to find that curve of intersection. So set x equal -2 equals to 6 minus 4y squared minus 4z squared, which is also equal to x. So setting these two pieces equal to each other gives us y squared plus z squared equals 2. So this is a circle of radius 2, so a parameterization r of t is equal to -2, because we know our x bound is -2, comma, √2, that's our radius, is √2, sine of t, √2, cosine of t. You could switch the sines and cosines, it doesn't matter as far as the function goes. And the parameterization. R prime of t, this just ensures that we go counterclockwise around a circle in a direction that works for us later. R prime of t is 0, √2 cosine of t, -√2 sine of t. So then our vector field f, evaluated at r, is equal to 2 cosine squared of t minus 1, √2 cosine of t plus -2 times 2 to the 3/2. I'm neglecting some simplification here. Sine cubed of t, comma 6. So if we dot f with r prime, f of r dotted with r prime of t, this gives us 1 plus cosine of 2t minus, let's take a step back here. Instead of 1 plus cosine of 2t, this gives us 2 cosine squared of t minus 8 cosine t sine cubed of t minus 6 √2 sine of t. And this is the thing that we'll have to evaluate. So this piece right here, this is in Stokes' theorem. Because when we're evaluating the curl of f dotted with ds, this is the same as evaluating over that closed curve of f dot dr. So we found the curl, instead of finding the curl of the vector field, we found the vector field and we found the curve of intersection of the two surfaces and the vector field, and we're looking at the circulation across there. And here our curve, we should say our time goes from 0 to 2 pi for our circulation. So we get 0 to 1, 1 plus cosine of 2t. This is our first component with an eye towards integration. Now we can make a nice U-substitution. Minus 8 cosine t sine cubed of t minus 6 √2 sine of t dt. So evaluating this, and we get 2 pi. So as always, if you have any questions, feel free to let me know.